Is the 27th of September, a Wednesday, and we are beginning our discussion of Chapter 4. I've laid out a schedule. Today we'll start Chapter 4. I'm going to show you what we're going to cover in here, and then we'll start to cover a little bit of that material. We will not have class on Friday, so there will be no vodcast, no class on Friday, and then we'll cover Chapter 4 in earnest next week. And the following Monday, so we have all of next week, Monday, October 9th, we will review for our midterm on Wednesday, the 11th of October, and our midterm exam, which is an in-class exam, will be on the 13th, Friday. We don't have a day off at midterm this year because we're getting the entire week off at Thanksgiving. I think it's a great trade, but there's no official day off, but we will be posting midterm grades so that you guys, or midterm progress reports is what they really are. They're not official grades, but they kind of let the students know where they stand and so forth. All right, so Chapter 4 is entitled Pure Bending. And the topic of pure bending, we're going to isolate some geometry to begin with. And then we're going to do one really interesting application. Not all today, I mean over the course of the next couple of weeks. But pure bending is a type of configuration that does not happen routinely in real life. It's actually coupled with a different type of a geometric configuration, but we are not going to use that at this time. We're going to break it down and isolate one of them first. So in Chapter 4, Chapter 4 consists of 10 sections, but we do sections 4.1 through 4.5. We eliminate 4.6 through 4.10. We don't cover these sections. And we need to look at the main focus after we get the basics down are actually in section 4.4. It's a very important application of this idea, and the most important application that we cover is how to analyze reinforced concrete. So by the time we get there, you'll have a lot of background knowledge that we'll be able to discuss and bring into the conversation. But the reason that reinforced concrete is such a big deal is that as engineers, so many things in this world are built using reinforced concrete that you need to have some ideas about the way concrete behaves and what we do to make it behave the way we want it to behave. So this is the basic material that we'll cover. Your textbook shows that sections 4.6 and 4.10 are optional, but that 7, 8, and 9 are required or not optional. They're just sort of topics, but we actually start to cover the idea of eccentric loading in a different area that at the end of the semester. So for now, 4.1, 4.5, and that will be all the material we'll cover before the midterm exam. All right. So first of all, let's talk about this idea of pure bending. When we talk about pure bending, what we are talking about is isolating a particular type of a deformation. And there are a couple of examples that are given in your textbook. But one that is applicable, although not widely used, is if you are lifting free weights at the gym, for example, and if these weights are equal to each other, and if you place your hands the same distance from each weight, what happens is the weights push down with a particular force, and with your hand and arms, you push back up with equal and opposite forces. And this type of a force system, where you have forces that are equal and opposite in sense, separated by a distance, is referred to as a couple. You may remember this from statics. Don't want anyone to start sweating. We had talked a lot about the idea of the last statics review we did had to do with finding, using the method of sections and the method of joints to find the forces and structural members of a truss. This is not that hard. This is just a really quick little review. So if you haven't seen couples, I'll teach it to you in just a couple of seconds here. But if we have a force, let's just say that this weight is 50 pounds, and you push back up with your body with a 50-pound force. You can see that from summation of forces in the y direction, that would be 50 minus 50 equals 0 pounds. Okay, so this does not produce a net force. But what does it produce? Well, it produces a tendency to rotate, doesn't it? So there is a moment associated with this couple, and that's referred to as the M of C. This particular couple, as you see, would rotate if it was not opposed. It would rotate counterclockwise, so that's positive. And this moment of the couple would rotate the other way, preferentially, clockwise. And so we still have a 0 net moment. But the first couple, let's just call this number 1 and this number 2, is equal to the magnitude of the weight, or the magnitude of the force, times the distance that separates those two. So the distance between the center line of the weight and the center line of your hand, let's just say in this case it's 1 foot. I'll just go ahead and diagram that, okay? And that means that the moment of that couple is 50 foot-pounds, okay? This, number 1, is going to be positive because the rotation would be counterclockwise. The moment of the couple 2 is going to be negative because its rotation would be clockwise. And the two oppose each other, equal and opposite in sense, just like the forces. So overall, I should put this, sorry, minus 50, because there's actually 4 forces, 2 couples. So we have moments that add to 0, forces that add to 0, which means, of course, that nothing's moving, nothing's rotating. So why are we interested in it? Well, the reason is because this force system, this force couple system, produces a bend in the bar, doesn't it? In other words, especially we're interested in the distance, the span in between the application of the forces of the couple, but we have a bend in the bar, and that's what we're interested in analyzing. So if you think about this, if the bar used to be a certain length, let's just say it was 2 feet, and I have no idea if these are human proportions or not, I'm just talking about a bar that's 2 feet long. If we were to draw a line through essentially the middle of this bar, what could you say about the length or the del above that line? Do you think it's going to be positive or negative? In other words, do you think that the bar will lengthen or shorten above the line? It will lengthen. And how about below the line? Think it'll compress a little bit? Yep. And if we could identify the location of that line, del at that line would be equal to 0. Wherever that line exists, where there is no deformation, that is referred to as the neutral axis. Okay? When we have this type of a couple system, where we are bending it into a convex, concave, convex upward motion. This is a negative force couple system. This is a negative M, I guess you would say, because of the net effect of the bend. It's a little bit, later on we'll introduce a more rigorous system. If we had a different kind of a bend, it's a little harder to exhibit talking about a free weight, but say that we had a rectangular structural member and we put C-clamps on the end of it and we pulled it up this way for some reason. Okay, this is referred to as a positive moment. Okay, or a positive bend. It's a positive, I don't know how to describe it, because it's just a geometric construct. But the way to remember this is, even though this is really silly, you'll never forget it, this looks like a frowny face and this looks like a smiley face. So smiley faces mean that you're positive and frowny faces mean that you're negative. Okay? So I swear to goodness I've had practicing engineers come back and tell me that they still remember it that way 15 years later. So you may not want to say it to your colleagues, but it's a good way to keep it in mind. So if it's bent downward, it's negative. If it's bent upward, it's positive. All right. Well, let's get a decent sheet of paper first. Let's take a look at if this is not a free weight bar anymore, but it's a prismatic beam. In other words, it started out in the shape of a square or a different type of a rectangle. If we subject it to a positive pure bending moment, if we bend it up like this, we know that the lower part of the beam is going to, in this case, lengthen, and the upper part, the part above the neutral axis, is going to shorten. And when that happens, if we look at the cross-section, the cross-section is going to do the opposite. In other words, where it shortens on the axis, it will lengthen here. We know that from studying Poisson's ratio. Where it lengthens here, it will shorten here. Now this is greatly, greatly, greatly exaggerated. The actual trapezoidal nature is going to be quite subtle. So let me draw something a little more subtle, like that. Okay? And what that means is, because we just love geometry as engineers, we can think of this beam as being bent in a circular fashion, having some center of curvature, and that if the axis is bent into some sort of a center of curvature, then the cross-section is bent into some sort of a curvature as well. So this is just referred to as the center of curvature. And of course, you may be thinking, in real life, this is like an impossible location to identify. And it is. This distance from the neutral axis, let's do this. The distance from the neutral axis here to that center of curvature is identified as rho, which is called the radius of curvature. And although we'll discuss what that distance is, it's not a number that you would ever really find. It's a number that we use to develop some other equations. And they call this distance rho prime. And for reasons I do not fully understand, the reciprocal of rho prime is referred to as the radius of anticlastic curvature. I don't know why it's the reciprocal, because it doesn't even have units of length, but there it is, just the same. All right, so when we bend that, we can identify, we'll learn how later on, we can identify the neutral axis on both the axis and the cross-section. And we can also recognize that on our original prismatic member, that we're really not talking about a line, we're really talking about a surface, aren't we? A surface that remains undeformed. And so we can refer to that entire two-dimensional surface as the neutral surface. Okay. The other thing I would like to point out to you, on page 243 of your textbook, they develop this idea, but I want to show you something that is not wrong, but it's confusing or misleading. When they bend this prismatic member so that it is concave up, if they were to bend this prismatic member and the top part of the beam were to shorten, the top part of the cross section would widen, wouldn't it? So in other words, this picture does not go with this bended structural member. This is not incorrect, this is not incorrect, but the two are not the same bent structural member. Okay, so if you look at that, just keep that in mind. That's why I always make a point of drawing it the correct way, because like I said, this is not incorrect, but it is misleading if your mind tends to put these two together and think this is cross section, and then you go, wait a second, that's not correct. It's not correct if you think about it that way. It's only correct if you think about one and then the other. So if you're thinking about them together, this would go with this type of a deformation. Right. And they actually kind of draw this out for you in 3 dimensions on page 249, where they draw the neutral surface, the axis, the cross section, and you can see what we're talking about. This shortens, so this lengthens. Have a center of curvature, anticlastic curvature, and curvature, the radius of curvature. Okay. And so, like I said, this is the other part, and I think maybe I'm going to stop here today because I just want you to ponder these things and finish chapter 3, and we'll start this on Monday. As I said, the radius of curvature is rho, but rho prime, which is the distance from here to here, is not called the radius of anticlastic curvature, but 1 over rho prime is called the anticlastic curvature. And it turns out, you may have been able to think about this, that it would have some feature of Poisson's ratio, because that's what relates geometric changes on the cross-section to geometric changes on the axis. Turns out that it's equal to nu over rho. So that means since nu is a little number, when we divide by a big number, this number becomes very large, because we have a little number and a large number, so this number becomes very small. I'm sorry, I said it the wrong way. So anticlastic curvature is the opposite almost of what I would consider to be a radius. It's the reciprocal of a radius. All right. Do you guys have any questions at this point? Let's not have any homework tonight. We'll have an easy couple of days. So I'll go ahead and turn off my streaming.